Geometric sequences. So geometric sequences tie nicely into exponential functions because identifying an exponential function, if you say yes or no, that's exponential. If we look back in our notes to exponential functions, what makes it an exponential function? Zach?
When the y values are being multiplied or divided by the same value.
Yeah, when your pattern in your y value is a multiply or divide pattern. The x pattern still add or subtract, but the y pattern is multiply or divide. That's an exponential function. Meaning if you graphed it, it makes a curve, correct? Geometric sequences are just another name for exponential functions. Basically, the difference is exponential functions like have a relationship. So you'd talk about like our question we did this morning of the rate of decay of polar bears, right? There's a relationship with it. Geometric sequences are when there aren't any labels to it. It's just a random pattern and they're asking you, is there a pattern to this set of numbers? Okay? Probably should have done this before we did exponential functions, but you know, everybody makes mistakes. All right, so exponential functions. Or geometric sequences. See, now I'm going to screw it up. A geometric sequence, the key is that there's a ratio of successive terms. And the ratio is important because it's not an add or subtract ratio, it's a multiply or divide ratio. So it's a ratio of successive terms, and the ratio, meaning the multiply or divide number, right? The ratio itself, the number, the patterning, is called the common ratio. So there's a little bit of vocabulary in here that's a little different. So like, you know, before we called that the y, the change in y, which is totally fine. It's also sometimes known as the common ratio. So just the multiply number, the change in y is called the common ratio. So maybe I'll put that in parentheses too. It's really just the change in y. What we've known as. Now, unfortunately, a geometric sequence is just a pattern of numbers, so it's not an ordered pair, so it's a little harder to sometimes tell. Maybe not. I guess I'll let you make that decision. So for an example, now on purpose, I'm leaving a blank line, and I'm writing my geometric sequence below. Okay? So if I had 3, 6, 12, 24, 48, 96. We'd say, is this a geometric sequence? You'd have to figure it out. Like, is this a geometric sequence? So there's some vocabulary that we can talk about with it. And that vocabulary is, sorry, I'm trying to find a different color. The numbers in the pattern are called terms. So these numbers are called terms. And it's kind of hard to talk about them without talking about their position. So we've got terms and we've got positions. And it's pretty self-explanatory for the positions. 3 is in the first position. Or it's the first term. So in this exact pattern, 6 is the second position, or the second term. Third, fourth, fifth, sixth, and so on. You can also write it algebraically, which you're going to see sometimes. So instead of writing it's the first term, you'd write A for amount, and it's A1, subset 1. And this is A2, A3, A4, A5, A6, right? They're not exponents, they're subsets, meaning they tell us a position. They're not in the problem, they're markers of the problem. And this is the algebraic way of talking about it. So is this a geometric sequence? Does it follow a pattern?
Yes.
To get from 3 to 6, what do you do?
Multiply by 2.
Multiply by 2. From 6 to 12.
Multiply by 2.
12 to 24.
Multiply by 2.
24 to 48.
Multiply by 2.
48 to 96. So if I said, what's the 8th term, could you figure it out?
Yes. Yes.
Yeah, you just keep multiplying by 2, right? If you did this and it was multiply by 2, multiply by 3, multiply by 2, multiply by 3, multiply by 2, multiply by 3, is that geometric?
No.
No, because it's not constant. It's not a ratio, a common ratio, right? It changes every time, or changes every other time. If one of them's multiply, then the rest are divide, no. It's not geometric.
Wait. So could you figure it out by going backwards by saying there's a 1.5 before the 3?
Right, so if like these two were missing, could you figure out what the second term is?
Yeah.
Yeah, because moving to the right, you multiply by 2, but moving to the left, you
Divide.
divide by 2. You do the inverse of it.
What would, if 12 was labeled as the first position, would they be like...
It's still multiplied by 2.
I know, but... So if you didn't have 3 and 6, but 12 was the
Uh-huh.
first position.
12 is the first
and you
position.
went backwards. Could you get the other two? Or
Uh-huh.
what
Yeah,
position
you could
would
do,
they be?
it'd probably be negatives. Okay? So we can write a formula for this. And follow along with me. Don't freak out yet.
I'm freaking out.
There's a formula for this. If I said, like, write the formula to predict, what if I said I want to know the 102nd number in this term? In this sequence, I want to know the 102nd number. Do you really want to sit there and times by 2 all the way up 102 times? No, that's crazy. I mean, you could. Or you could use this formula. Now, here's the formula. AN equals. Now, some people have a hard time when I put AN. So what could you put there? X or Y or f of x, right? Anything. The answer. That's just the answer. The number that we're looking for. A1, what does that represent?
The first position.
The first number, the first position. So in this problem, it would be 3. Times R. What does R represent?
The rate.
The rate, the ratio, the common ratio that we found. And then the number we want, n minus 1. So now let's label those. Again, that an sometimes scares people. That's just the answer. If you don't like having an there because it's scary to you, could you put y? Could you put f of x? Could you put the letter q? Could you just put a for answer? Right? It's the nth, the mystery number, n standing for number, term. It's the mystery. It's the nth term. If I'm looking for the 100th term, this is the 100th term. If I'm looking for the 91st term, this is the 91st term. A to the first is just the first term in the pattern. R, I'm going to circle it because it kind of gets smushed in there, is the common ratio. And the common ratio is the multiply or divide number. And then n minus 1, n is the number we are looking for. So if you're looking for the 100th term, you put 100 in there. 100 minus 1. Sounds about right.
Maybe we'll get some.
Amen. All right. Questions?
No.
Let's practice.
Wait, that's the whole lesson.
Well, I mean, we're going to do it like in a couple examples. Okay, so let's talk basics. If I give you 9, 27, 81, 243. Blank, blank. Let's talk basics to begin with. First question. What is the first term? Is this scary?
Yes.
I know, right? What's the first term? What's the first number in the pattern? 9. How do I know?
It's the first number.
It's right here. It's the first thing. What is the common ratio? So you look at them, you say, okay, what do I do to 9 to get 27? What do I do to 27 to get 81? What do I do to 81 to get 243?
Multiply by 3.
Multiply by 3. So the common ratio, I still like to put, oops, forgot I was doing this in a different color. I still like to put the operation times 3. Just because it helps me remember later on that I'm multiplying. But, I mean, you don't have to. The common ratio is 3.
This one you could divide if you wanted. Like, you could get this yours term.
What is the 5th term? How do you find the 5th term?
Use the formula.
Dylan, what do you do?
You use the formula.
You what?
Use the formula.
Okay, you could use the formula, or since it's just the 5th term, right? I could just take the 4th term and multiply by 3. What is it?
729.
729.
So, what is the 11th term? Now, 11's not that much bigger, right? But here's the deal. Sometimes our attention span isn't very long. And multiplying by 3 up to 11, you might get to like 9 and then be like, oh, what? What number was I on? And have to start over. So let's use the formula for this one. So, to find the 11th term, a to the n, that's just my answer. I don't worry about anything that tells me I'm looking for the 11th term. That's going to be my answer. If you don't like it, y equals. All right, a to the first. So what's my first term?
9.
9. So 9 times, what's my ratio?
3.
3. To the power of
10.
n minus 1. I'm looking for my 11th term, so 11 minus 1. 9, my first term, times my ratio, which is 3 in this problem, to the power of, I'm looking for my 11th term, so I'm doing 11 minus 1. Use a calculator. Dylan, what'd you get? 531. What? 44 1? This?
She wrote a Y.
Okay, try this one.
Oh.
128, 64, 32, 16. I want to know what is the 12th term. Now here's where the tricky part comes in. Here's where the hard part comes in, because you think to yourself, Mrs. Long, wait a second. 128 to 64 to 32 to 16, what's my common ratio? We're dividing by 2. My common ratio is not 2. My common ratio is dividing by 2. Dividing by 2 is the same thing as what?
-2. 1/2.
1/2. Multiplying by 1/2. So even though we talked about it's your multiply or divide number, it really needs to only be the multiply number. If it's a divide, you have to figure out dividing by that number is the same as multiplying by what?
So they're reciprocal?
So it's the reciprocal of it.
So if it was divided by 3, what would it be?
What's the reciprocal of 3?
1/3.
Take 3, make it a fraction,
Oh,
over 1, right? And flip it upside down. So the reciprocal of 3 is 1/3. If it was divided by 4, what's the reciprocal of 4? What?
When?
1/4.
When did this happen?
If it was divided by 5, what's the reciprocal of
Sort of thought that
divide
was
of 5?
Okay.
1/5. So since the common ratio is divide by 2, that's the same as times 1/2. So my common ratio is times 1/2. I don't want to put divide, I want to put times 1/2. So I'm going to put y equals the first term. What's the first term in the problem? 128 times, what's the common ratio? What do you do each time?
1/2.
You divide by 2 each time, but I want the multiply version of it. Instead of divide by 2, times by 1/2. And my exponent is 12 minus 1. What's the 12th term? It's little. Sam? 0.0625.